questions on, if anyone has questions on two of today's talks given by George or Yvette, we could maybe start there. This would be a good time to discuss those. And while people think of their questions, I could start with one of my questions that I had for Yvette.
Yes.
That was related to the sensitivity formula that you were showing in your slides. I saw a dependence that was something like L to the 7/2 in your sensitivity to strain. I was wondering if you could give a physical intuition for that.
Do you want me to upload the plot maybe, because we can see?
Yeah. The slide that had the sensitivity and the formula, if you can share.
Yeah.
I can also try to pull it up. Oh yeah, there you go.
So that is this one.
20. Yeah, this one, yeah.
From current slide, yes. So when we first start writing the formula, we have it in terms of the scattering length and it's just because we start like rewriting things in terms of the parameters that we can manipulate in the lab, the ones we have at hold, and it's a bit like how things combine. So it's not like a intuition of what at the end it depends at. This is L to the 7th is when I wish I had some more details of that here. It's kind of how things combine, because several of the different parameters, like the scattering length and so on, depend on.
But this is still the size of your detector, right? So to measure the gravitational wave, you would have to be proportional to the size of the detector.
So yeah, so what's going to change quite a lot with the length of the gravitational wave detector is like what frequency are you sensitive to. So the mode that you're resonant to depends on the speed of sound. It's like the speed of sound divided by the length of the gravitational of the detector. So that's where you have these combinations of L's, because the speed of sound is also going to depend on the parameters of the BC, and it all sort of combines. But in this reference here, and I put the paper on the discussion, there you can see how the details of how we derive this, and you can see how first we're writing things in terms of I'm trying to see why, because then we have the speed of sound. Yeah, so we got everything started by the speed of sound divided by the length of the trap, but then we want to write the speed of sound in terms of, you know, the parameters that you can change. So we wrote the speed of sound in terms of the scattering length. So that's where you get, you know, the different L's. But if you want to change the frequency, you change the length, but that's also going to affect your sensitivity.
Yeah, okay. And then another thing that you said was that in this method, you're not really measuring the direct change in space-like distances, but you're measuring change in delta T that's caused by the gravitational wave. So typically the change in...
I didn't hear the last thing you said, that I'm measuring what?
The change in time caused by the gravitational wave, right?
No, it's we looked at so you have that's what also Valerie was asking about. So you have, you consider the BC to be like a rigid trap. So then you can, you know, calculate what happens to the modes inside the box for a rigid box in either the TT frame or the detector frame. But we're now doing, the first paper we did in the TT frame, but then we realized it was all much simpler and also more direct with respect to discussions with the experimentalists to do everything directly beginning on the proper detector frame. And we're looking at how the space-time changes with the metric that I showed to you, changes the state of the phonons living on it through the Klein-Gordon equation.
But it's changing, you're measuring the change in the physical size of the box. Is that correct?
Oh, I guess that you can see, I guess, like here in the metric, no? So this is the line element, and this is where the perturbation comes, and this is what's going to be changing. So what I do is, like, I have a Klein-Gordon equation in this metric, and I solve that Klein-Gordon equation in this metric.
Mm-hmm. Okay.
So maybe in this case it becomes very simplified, but then when you do it, so we have a new paper, I'll put the link on that too, which is much more general. It's not just as for gravitational waves, but we solve an example for now a 3-dimensional box. And there you can see much more and more like the tensor structure of the gravitational wave, and then it's a little bit more involved and interesting in that case. But it all comes from solving the Klein-Gordon equation in the metric of the gravitational wave using Bogoliubov transformations, then to relate initial and final conditions.
Okay, so I think Danny and Andy have something to say. Let's hear from them. Danny, okay. You want to go first?
Hi, do you hear me?
Yeah.
Okay, I'm sorry, I cannot use my camera right now because it's not working. But, well, you get to see a beautiful background of Valencia at least. So I also have a question about these sensitivities that you are showing, Yvette. So if you can go back to this transparency. I have comments and questions. You know, the first comment is that I'm really impressed about these numbers you are showing. But let me make sure I'm understanding, okay? By sensitivity here, you mean the strain, the actual perturbation on top of the Minkowski metric you can measure? Is that what you are
This is really... the characteristic amplitude.
The characteristic amplitude.
So I'm looking like here, you can see the metric. This is this epsilon here, no?
Yeah, okay, so it's the actual amplitude of the perturbation on top of Minkowski. Fantastic, okay. So I think these numbers are amazing. Maybe I'm getting confused right now, but I think it's the first time I see an experimental prospect showing such a capability for experimental constraints, okay, at these high frequencies, okay? So first comment is, I think this is very impressive. I was trying to do a quick conversion, back of the envelope calculation to convert into omega gravitational waves, because you know, theorists, cosmologists, very often we think in terms of omega gravitational waves. And if I'm not mistaken, your purple curve at the megahertz with the sensitivity 10 to minus 25, I think corresponds roughly to BBN constraint. Have you done this conversion just to know?
So, and this is, I mean, this is where we're meeting, right? Because I come from quantum optics.
Yeah.
And, you know, like that is sort of my background is very different. And I came up with this crazy idea, started to explore it, learned of gravitational waves. I mean, I have a background on gravity. I did a lot of things on relativistic quantum information and things like that.
No worries. Understood.
I'm meeting you guys sort of for the first time. So this is the sort of thing that why I'm so interested in this interaction, because if you tell me, look, we don't present things like that. We use the cube.
No, it depends on the person. It depends on the person. Maybe it's my own bias, you know. Because
no, that's good, because there's something happens to me that for me to understand something, sometimes I need to see it in terms of what I'm used to. So I'm very happy that if you email me, we can translate some of these things. And also maybe there's things that I don't do as they should be done. So I'm happy to learn from you guys and kind of try to improve on that. No,
I will send you some basic formula references, and then hopefully
that would be great.
This.
We solved this problem of units in the last meeting. We decided that the units are basically decided by the source you're looking for. So yeah.
But okay, if I'm not mistaken in this quick conversion I made, this would imply that at megahertz, you are having sensitivity, at least implied by your purple line, the lowest one, of roughly what is called the BBM bound or CMB bound. And okay, that might not be sufficient to characterize so-called cosmological backgrounds, but I think it's an impressive step if this gets to become real towards that direction. So then my final question is, what is the time scale realistically that you guys could build something like this? Are we talking about something that could be operating within this decade? Or there is a lot of factors here that you don't really control? It's not clear to what extent at the experimental level this can be realized.
So look, I mean, Bose-Einstein condensates, there's many.
Yeah,
already built in the world. This needs high number of atoms, around 10 to the 8, 10 to the 9. Because of atom interferometry, it became not very interesting to have so many atoms anymore. So people focused in 10 to the 6, 10 to the 5. But there's papers in from 2007 already with sodium, a paper in the Netherlands, where they got 10 to the 8 atoms. So that is possible. Most groups don't have them so big, but for example, I was talking to Chris Foote, who is in Oxford, and he has one BC with strontium with 10 to the 8 atoms. And he was saying, well, let's talk because I don't know what to do with it.
I see.
With so many atoms, what can I do with it? So one of the things that you need to do is have high atoms. So that already exists. The square potential already exists in Cambridge, but with few atoms, with 10 to the 5 maybe, or maybe 10 to the 4. So it's a little bit like all the ingredients have already been done in one way or the other. What has never been done is put all these ingredients together.
Yeah, I see. And along the same line, then, would it be realistic to think that you could even in the near future, do an experiment with even more than 10 to 8, which I assume is the good direction to improve sensitivity?
Yes, I mean, the main thing with the sensitivity would be to get this lifetime of the phonons longer. So there's the 3-body recombination. There we would have to do theory to find out ways of, let's say, reducing. So for example, one of my students just wrote a thesis. I think I put this one, that he on his own came up with an idea on how to reduce 3-body recombination, because he noticed that there were some for lithium, that is something called Efinov resonances, and that if he used that, there was like a dip that he could use in order to get a reduction on the and get longer phonon times. So that is where we need the support of the community, doing those sort of studies to say, okay, what do we need to do? We need to put more atoms in the BC. There's no fundamental reason why you cannot put more atoms in the BC. Of course, it's more difficult, but that would be one line of avenue to move towards that. The longer phonon times, also the squeezing, for example, that is a big question as well. How many phonons can you actually squeeze in a state? Is also unknown. That's what I'm working with Chris Westbrook, who's the experimentalist in Paris. He's we're putting another Synergy grant together to study that. So there's a number of things, but no, I liked what it said here about the conference, that the aim is kind of getting the support from the community, and I think that is what is needed here. Work in different directions to get those things working.
I agree.
Here, these numbers now consider, when we first started with a proposal, the numbers were already very good, but then we hadn't studied a lot of sources of noise. So when we started to add sources of noise and put shorter phonon times, which were more realistic, we lost a lot of orders of magnitude. And that's where then we came up with this idea, which I put in the paper, which, the first proposal was just squeezing 2 modes and measuring. That's all we did, was like squeeze these 2 modes and then you measure. And then we found in another paper on quantum optics related to photons, not atoms, that people were using this triter, and we said, oh, this might work here. We added this 3-way combination, and we won more orders of magnitude of what we had lost. So
Okay.
this is kind of the what's happening with a new idea like this is that, you know, you get something, then you make it more realistic, you'll lose something, but then you can still be smart and creative and find ways of increasing the let's say, for example, the scaling with the number of resources that you have and get better sensitivities.
Well, it looks in the right direction, so thank you very much, really.
Thank you very much.
Very interesting.
Thanks.
So Andy, you want to go next?
Yeah, thanks. I just had a follow-up question on this same topic of sensitivity for this scheme. So very nice talk, Yvette. If we could go back to the old slide you had up with the sensitivity formula, yeah. Great. So L here is sort of the length scale of the experiment, which I guess is set by the optical trap or whatever kind of means you're confining the BEC. Is that correct?
Yes, it's the length of your BEC. Yeah.
So can that be used? I guess I have a couple of questions. So first, can that be used to sort of mitigate this 3-body recombination issue, because you can sort of keep the same number of atoms but extend the size of the volume to limit that rate? So that's my first question. And then my second question is more in terms of the environmental noise or other kind of backgrounds that might also cause problems where you could cause excitations that might otherwise limit your sensitivity or even look like an excitation from a gravitational wave. In particular, do you have to worry about things like vibration or technical noise, or how about decoherence in the two-mode squeeze state from other kind of decoherence mechanisms?
Yes. So, well, let me first answer your first question. So if there's always, like, things are connected, so there's always a trade-off. So if you change the size of the BC, you'll make it obviously more dilute, and that will change the speed of sound. And you need, that's where this optimization that my postdoc did for me, because, you know, you tend to think, oh, if I get, you know, higher speeds of sound, it will work better. Yes, but then, I mean, you could end up in a situation in which you have a very high density. And if you have very high density, then you have a super high particle loss due to 3-body recombination. So that's where we played here in the optimization, was trying to find an optimal for the length and the scattering length and so on. So yeah, it's always that playing with that. So these are all the parameters that come about, and like I said, they're connected in these ways. But then you have all the constraints, and here are the constraints. So you're dealing with phonons, so you need to look at the scattering at the not the scattering length, at the dispersion relation. So you need to be in the phonon regime, and that puts some constraints again on the length. As you can see, I don't know, my cursor, my pointer is not working, but the last where you see phonon regime. So then you have some constraints there on the length and on the scattering length again, and you're in the ultra cold regime and weak interactions. So we looked at, for example, 2-body losses. So this is decoherence. So we have this paper that is a bit older where we studied in general terms different sources of decoherence. So these are all the Bilev and sorry, my pronunciation of that is so terrible, but the 2 different 2-body decoherence effects, as well as 3-body recombination is also decoherence. Thermal effects. So if you just look at what happens with the thermal state before you get started at 0.5 nanokelvin, that almost doesn't play any role. However, what does play a role with the temperature is that will make the preparation of your squeeze state and the phonon lifetime more complicated and shorter. So we have studied quite a few sources of noise, but I guess there's still more to be studied. And that is what we're doing with Chris Westbrook and Philippe Boyer, because I think we studied as many as we could in terms of general parameters, but now you need, what we've been doing with them as well is trying to pick what would be the optimal species and then go more into the different noises even further, but for that specific implementation. So if you could, you know, spot some source of noise that you would like me to study, that would be also something that could be very helpful.
But something like, say, the environmental background noise for vibration or something like that, is that likely to cause a problem with the jiggling of the optical trap or something like that? Or
So, well, we've had some of like, what we did include is like, you know, collisions with other things, atoms or molecules or whatever in the trap. That sort of environmental ones we looked at. We've made some rough estimations of trap instabilities, but I think in that direction, that's where we still need to look a little bit more into trap instabilities.
Thanks.
So I see a few hands here, but I'll just make a quick announcement that I am not the best person to ask questions to Andy and George because I work with them. So if you have questions for them, please raise your hands. And also Nicholas Herman has also joined us. So if you have questions about that design, please let us know. So George, do you want to?
One more thing about this, like, sorry, this trap instability and the noises from, let's say, vibrations and so on, is that since this works on resonance, the noises that we need to worry about are the ones close to the resonance. So I think things like seismic noise and stuff like this is quite far from these frequencies. So more things like the laser instabilities and stuff like this could be more relevant at high frequencies. But that is, since it's a resonant detector, I think that is also something that helps in terms of noise.
Okay, George.
Hi there. It's a kind of quick, simple question that might be a silly one, and you might have already answered it. At what number of atoms does self-gravitation become an issue, right? Like if you really use 10 to the 8 atoms, 10 to the 9 atoms, is there a point where you start creating your own signal in your kind of BEC bath?
So you said, so if you have more than 10 to the 8 atoms, or 10 to the 9 with the parameters we picked, like with the sizes we picked and so on, then your densities will be very high. And then your phonon lifetimes will be very low. So we sort of optimized on that. But then, George, sorry, I didn't hear very well the rest of your question.
If you keep increasing the number of atoms in your system, does self-gravitation become an issue eventually?
Self-gravitation?
Yeah, like, I mean, at 10 to the 9 atoms, that's sort of an equivalent mass to the nanoparticle you proposed to test your system earlier. I mean, for a 60 nanometer particle. So I'm curious if your bath starts sort of attracting itself, right? Like if the right-hand side starts attracting the left-hand side. I mean, I guess the frequency domain of that process is very different, but I'm curious if there's a bound at which point it becomes significant.
I think that would be much smaller, but I mean we can calculate that, but the only interactions that come into at the moment in the calculation are collisions, like, you know, yeah, just like particle collisions. That's a hard wall collisions. There's like no gravitational within considered in the model within the atoms, but I would guess that would be much smaller.
Okay, cool. Thanks for answering.
Yeah, Fernando.
Yes. Okay. Thank you. Well, again, a question to Yvette. Nice to see you, by the way, Yvette.
Yes, I was going to say that. Great to see you. It's been many years now.
Yes, that's good. So, no, this is the question I wanted to ask you when you're talking. Probably you have more or less addressed it in the last few minutes. But in general, what would be the limitations of principle you can have? So, for instance, how far do you think you can go with unlimited budget and in say 20 years from now or so? Or 50 years from now. Is there something that you said I cannot go beyond this because of some obstruction or some?
Yeah, you mean like something fundamental, no?
Like
well,
frequencies.
I guess with the phonon lifetime, at some point, I would guess it must become super difficult to reduce them and have, you know, because with the current situation, that is our most limiting factor, the three-body recombination. And we know that when the density increases, that's going to increase. And I think you might be able to play with it by adding fields finding some clever way to reduce it, but there should be a limit that you hit there, no? Mm-hmm. Then the other thing that you could do is get more and more bigger BECs with the right density. So you say, okay, I'm not going to increase the density anymore, but I am going to increase the size of the BC. So I think BCs are, the big ones are around 100 micrometers. And I don't think we know if we could do like, I don't know, a much bigger BC, 10 times bigger. I don't see a fundamental reason why not, but I don't know of one. Now, the other thing where I am very interested in exploring beyond this is that this is say an implementation using a Bose-Einstein condensate. But as I mentioned before, there is no reason why this should work only in this system. What you need is a system that has modes, and modes in the quantum regime. And basically, if you look at the key idea, there are very few ingredients that you actually need to do it. So this is what I want to explore, because in superconducting circuits, you also have like a box cavity and you have phononic modes. And in principle, one could explore what happens there yet. So I think this is very new. And in principle, it has many different branches where we could explore possibilities.
Very interesting. Thank you.
Thanks.
Francesco, go ahead.
Yeah, I had a question for Nicolas and Sebastian Klesse, who is in the audience as well, and is giving a talk about the same concept tomorrow. Do you already have plans to put your proposal in a lab? Have you got in touch with some experimentalists, or what's the situation?
Not really. We don't have at this time any concrete contact to set up the experiments. So this is why at the end of my talk I said that we need interaction with experimental physicists to make this more concrete.
Okay, thanks.
Hi, Sebastian. So along the same lines, actually, I think it would be good to discuss for all of these three experiments, levitated sensor detectors, BEC, and the electromagnetic conversion detector that Nicholas talked about, what kind of timelines and common technologies can be anticipated? So I saw that George had a timeline in his talk. So Yvette, have you guys started building these detectors?
Let me unmute it because some people started to arrive from school and work, and it got a little noisy here at home. Yes, well, we've been applying for money and making proposals, you know, kind of really looking at, I mean, building an experiment from scratch. Because if we used one already existing, there are some people interested in that. Like, for example, Adrian Arnold in Strathclyde already has a BC, and he says, okay, if we get the money, I can use my BC. But if we also, like, I have a lab in, I almost got money, and Southampton gave me a lab, and then the money didn't materialize at the last moment. So I have a lab, which is empty now. But if we did it from scratch, let's say, in that way, it would take like 5 years or 4, something like around 4, perhaps. It takes 1 year to build a BC from scratch. Then another year to maybe get, you know, the Flecha's resonance working how you want. And the third year you would start doing things. And the first thing I would do is test it with the bead. So put the bead close and see that indeed the state of the phonos changes with the nearby bead. And I think that would take around 4 years, more or less, like in the best case, 4 or 5 years. And then from there on, we could then, you know, I would think between 5 and 10 years, maybe. But the test of principle could be 4 years. Now that I'm just thinking like, okay, I get like a grant, like, I don't know, 4 million, and I could do something like that in 4 or 5 years, no? But then to turn this into a serious thing, well, it would have to be a community effort, and it would have to be a lot more money, because you need to also not to do just one, right? For you need to do several, and so on. So that would be like a bigger thing.
So currently for you at Southampton, what kind of experimental, so you're an experimentalist yourself?
No, I'm a theoretician, but I managed to convince someone almost to give me money. Maybe that's why the last minute they changed. But well, we were of course going to bring someone from Philippe Boyer's lab to Southampton, someone already very senior within his group to kind of start the new experiment and stuff like this. What I wanted, or what sounds fun to me, is just to be really close to it, so I can, you know, on a regular basis comment and get involved with the experimental part as well.
Very good. Yeah, Sebastian, do you have plans to build this other detector?
Well, no. In fact, that was more a theoretical study that we did, and but well, this is just my opinion. But to my opinion, this kind of microwave cavity that Nicola mentioned, we could eventually use an existing one. I would just say that, okay, this experiment, this is basically ADMX with the magnetic field 90 degrees from what it is now, and so, well, the best way and the cheapest way to make such an experiment would be to reuse something. I know that this was done for Alps, for instance, where they have reused the laser and then the magnetic the magnets of Hera. I think so. Yeah, and so. I don't know if anyone has an idea where we could reuse an experiment that maybe has done its job, and that we could try to reuse it. That would be fantastic. But we are not planning to build anything at the moment.
Very good. Valerie, you wanted to say something?
Yeah, just a question. But I mean, if you're done kind of with your question. Yeah, so I was this is also kind of a question to maybe kind of all of you, and this is me as a theorist speaking. So I don't understand patterns, right? So I understand kind of archive and I understand journals to some extent, and I'm just lost with patterns, right? So I'm a bit lost just kind of finding the documents and then reading the documents. And I also like, is this something kind of, I mean, is there a risk that kind of patterns could, I don't know, like, for example, block, say that an independent realization of the experiment? Is this something like, because I've only come across patterns in this particular field. So I don't know if this is something which is just always there and I just never hear about it, or if this is kind of common, or kind of what is going on.
I can eventually reply for the kind of detector that we have proposed. It has been patented by a guy from the University of Namur. But when I asked him, I asked him the same question, in fact. So, and he just replied, no, it's the idea is just that the day we would like to build such an experiment, then the experiment will have to acknowledge that, okay, this was proposed by this guy at this group at that time, and we cite it, and we make these people involved in the experiment, basically.
But you
So
have to do the same
that's
thing.
the idea. So it's not a
papers.
question of money, for instance.
But it's the same thing for papers, right? Like if you're building something that someone else proposed in archive, you're still supposed to give them credit. So I completely agree with Valerie's question here, because it's so hard to read and understand this this design because of the patent documentation. It's a very different documentation style, right?
Yeah, but this kind of experiment is accompanied. There is a paper also on the design. Huh? So you should have a look at the archive paper, not especially on the patent documents.
Okay, so maybe the paper doesn't have as much detail as we wanted. So maybe that's probably still coming. And okay. Yeah.
For a theoretician or for someone who would like to build an experiment, I think you should start with the patent, not with the patent, but with the archive, with the article published on the archive.
So
yeah,
I
was
my
reading.
patent has nothing to do with the gravity. I mean, I first did the gravitational wave detector proposal, and then I thought, oh, this could be useful for local gravitational fields. And then someone convinced me to patent it, and I did, and it's been a nightmare because I don't understand anything from patents, and I hate talking to the patent officer. And I was like, anyway, but okay, I've learned, and it's been an interesting experience. But those are because those things in principle could be commercialized, and you could turn it into like a pocket gravimeter maybe one day in the far future, and so on. But yeah, but all of mine is with respect to gravitational waves is in the archive. Yeah, some of it is not even still in the journal because I understand archive better, like Valerie says. Oh, you asked me something about the vacuum, and I'm a bit confused about that, but maybe we can discuss it so you explain to me better the, I don't know if you want to discuss it later or now, whatever.
I'm happy to ask a question now, if I can ask another question.
Yeah.
I want to see, I think Andreas and Mike might have had something to say, so I want to see if they know.
Okay, yeah, well, just contributing to, I mean, I thought this idea, this Sebastian has outlined and Nicholas, extremely interesting, and it's revolutionary in terms of the way that electromagnetic energy seems to be generated in this detector compared to every other use of this inverse Gershenstein effect. So I think it's really important to try and make progress in understanding it. And I mean, I don't understand the patent business at all, but fair enough. The other thing I find difficult is that it's, it's all in the simulation program, really, rather than equations which one can look at and assess which modes really exist and which don't. So it's very difficult, really, to form an opinion on the viability of it until more kind of theoretical understanding of it comes forward, because at the moment these modes are generated in some kind of simulation program, and we just don't know how unbiased and accurate those simulations are. I mean, all simulation programs have a point at which they don't really work terribly well, either for numerical instability or because there are fundamental flaws. And I think to base the proposal on a simulation program, but we don't know what's going on inside it, makes it very difficult for people to contribute to it. And I think it's an idea that really needs to be followed up, and we hope it will work, and it's a very important idea. But anyway, I thought I would just say that I think it's the simulation program more than the patents that are the difficulty in understanding it at the moment.
I also, just to add to what Mike said, one thing is if simulation is the only way to calculate some of these questions, then perhaps it's worthwhile to show a benchmark of a known physics thing that your simulation can reproduce the benchmark. But I completely agree that the physics of the system don't seem that complicated that you wouldn't be able to explain in physical terms and would have to resort to simulations. And similarly on the arbitrary units, I think for stuff like gravitational waves, when you're comparing the signal from primordial black holes to the detectability from the detector, you can very easily convert that into strain, which would also give it a little bit more understandability.
Maybe I can answer a little bit about that. I will try to share my screen. Okay. So do you see the screen?
Yes, yes.
Okay, fine. So the main equation for the detector is this equation, which is a wave equation for the induced magnetic field. And that's the equation we want to solve. And to solve this equation, we project the the source term and the induced term on the proper function of the Laplacian operator, that and the proper functions respect the cavity boundary conditions. And then we have, for all the spectral coefficients, we have this harmonic oscillator equation to solve. And after that, we compute the variation of energy inside the cavity at first order. So we have the scalar product here between the external field and the induced field here. And with this, when we compute that, we show that only one mode, when we compute the integral on the volume, only the radial mode, so the K10 mode, will contribute to the variation of energy at first order. And the source term that are projects on the proper function of Laplacian is like this. And after, to solve, first we use a temporal approach. So it's an ODE solving. But now, after, we make a frequency analysis. So we solve the equation in the Fourier domain. And then we have the source term in terms of frequency. And then here, it's the root mean square induced power for just a sinus function in the cavity. And this expression is fully analytic.
Yeah, I think it's very important what you mentioned, Nicolas, because this can give some insight of so all the beginning was quite technical, but at the end, in fact, it's easy to obtain just analytical formula for just orders of magnitude, and so it's well, of course. You will need a follow-up of the simulations just to check that everything is correct and so on. But the theoretical part and this estimation of the order of amplitude that can be detected, this is something that everyone can do. Huh? So it's not particularly difficult.
Okay, so I think I want to continue discussing this, but that's just me, so I could do that on Mattermost. But if other people have other questions, we could do those. Or I was also thinking we could talk about a little bit big picture stuff about collaboration and forward steps for all the 3 experiments. Okay, so I see some nods here. So yeah, one thing that we want to ask when we talk with the broader gravitational wave community from other frequencies is what are sort of the common technologies that that experimentalists from these experiments can maybe collaborate on, or what are some common challenges that you guys anticipate having? And we already heard from Yvette about some of the challenges of combining these systems, all of these proven things into one system, right? Like combining. So I don't know if Andy or Nicola want to comment on what would be the most challenging thing for the other 2 experiments.
I think that the most challenging for these experiments, it's to have a constant magnetic field in the whole cavity. It could be a very challenging,
Because you are proposing to have a constant field over what volume?
It's a cylindrical cavity of 1 meter radius, or it could be 5, but we can anyway tune the parameters of our cavity and the resonant frequencies will be slightly different.
Yeah.
But the volume, it's, yes, order of meter in radius and meter also for the length of the cavity. So,
and field is like few Tesla or several Teslas over that volume.
Yes, it's if we decrease the intensity of the magnetic field, the response will be decreased also.
Yeah.
And
okay. Yeah, that is challenging.
Yes, and another thing for the measurements is to measure root mean square powers over short time delay.
Yeah, Mike, you wanted to say something?
Yeah, I was going to say, obviously it's difficult to deal with the magnetic field issue and get it kind of uniform and get it sufficiently strong, but you know, what you're suggesting at the moment is an instrument that is 1,000 million times more sensitive than anybody else has suggested for an inverse Gershon sign. So if you drop off by a factor of 5 or 10, you should still have a big smile on your face because this is extremely sensitive. So you could use these iron boron magnets and have a DC field produced by those, and your instrument would still be way more sensitive than anything else that's around those frequencies. So you know, it would be wonderful to have 5 or 10 Tesla uniform throughout it, but surely, you know, with the iron boron magnets, you could get a very, very high sensitivity anyway. But please be careful using them. They can cut your fingers off. So
I'm sorry to join. I'm sorry to join late because I had another meeting. So did you fix this issue of this being linear or quadratic, or is it still surprising?
I'm sorry, I can't tell who's speaking. Probably because of the video. Oh,
it's Diego. It's Diego. Yeah.
Yeah. Sorry. I'm in another workshop this week. And I was curious to know that whether you have agreed on the correctness of the result or not.
I think we agreed that the current things were not very easily understandable, and it needs a bit more work to be presented to the community in a way it can be understood first before we can even verify the correctness.
So you mean that the way the signal is computed?
Yeah.
Because the problem was isn't the problem what Mike Cruz was asking, that precisely when you take the power and you take the standard formula, you are taking a time average of the signal and not, I mean, otherwise you cannot use the formula of power being energy multiplying omega over Q, right? No, this is
yeah. So the first order term vanishes when you do the time average.
I guess that was the point by Mike Cruz this morning. So I wonder if you fix it now or you are still puzzled. Or...
No, we didn't discuss that in detail, but we discussed sort of the big picture about the overall problem in understanding the calculation. Yeah, but I completely agree.
But for the time averaging, since we project the equation on the proper function of Laplacian, we show that there is one mode that doesn't vanish when you do the average.
But the Laplacian is space. It's a space operator. And here we're talking about time averaging. It shouldn't matter.
Yeah, because you still have as a function of t in your equations, but after what Diego is saying, you want to do power, and that relates to your other question about measuring powers at small time scales. And I think that's where more work needs to be done as to what time scale are you proposing to take these spectra, and how do you actually account for those in your math correctly.
And related to that is exactly what electromagnetic detector you use, because if it's if it's a bolometer and responding to average power, these modes seem to give you nothing. And if it's responding to the magnetic field, right? Because I mean, the electromagnetic detectors can only respond to either power or field, right? So if it's responding to field, then I'm afraid you're not going to get this factor of, because you're going to be just looking at H on its own, not multiplied by this big number. So that's, you know, I'd love to be able to understand it more, because this is such an interesting idea. I'm not, you know, I haven't made up my mind one way or the other, but it needs sorting out, because it could be very important.
Okay, I see what you mean, but maybe in the article published in Physical Review D, there is an appendix with more detailed math about the detection principle. But if you want to, we can discuss it a bit more technically, I would say later, if you want to.
Yeah. Also on Friday, since I'm supposed to give a talk on cavities, but I have no work on cavities. I mean, I'm working on them, but so I think this is one of the things that I want to kind of, I mean, being external, I think is kind of the things that I want to write a bit clear, and maybe, I mean, at least in the calculations we are making, unless you can, if the magnetic field is not stationary, then the time average may not average to zero. So imagine that magnetic field is also, there's a mode, and there are two modes resonate, but this is not what you are having. You're having a homogeneous field. So I will try to at least see the way I see it, and as an external.
Yeah, that's perfect. Yeah.
Maybe we could propose as a follow-up of this conference to organize like a small working group to better understand all these concepts, maybe redo some calculations, additional cross-checks, and I don't know, prepare a paper a bit more furnished, or I don't know.
I think this is a good idea.
Yeah, I think
just to organize.
This would be a good outcome.
Yeah.
Of the
Yes, I am very motivated to participate to this kind of interaction, because in my university I have only a few interactions that I can make about this topic. So I'm very pleased if we can work with several other scientists.
Maybe both theorists and experimentalists, because
yes, should be
as theorists there are certainly thousands of details that we didn't think about, and so probably some are important also. So
yeah, very good. Valerie, you had something to say?
Well, just kind of to maybe just add to the list of questions that I have for Nicholas and Sebastian. So one thing that I missed it, but I didn't see it in either the paper or the talk, was really a sensitivity curve. So essentially the sensitivity to strain as a function of frequency. Because you showed the constraints for the black holes, right? For the PPHs. So in order to do that, I think you probably have what I'm asking for, right? As some intermediate step. And it would be great to see that. So, you know, so that we can kind of talk about the detector concept independent of the PBH scenarios. That I think would be super interesting. And the other thing which I was wondering about is if you, I guess you're considering kind of more like a response to, say, a monochromatic source or something like that, right? I wonder what would happen with a stochastic source, right? Also in view that kind of a stochastic background, you can turn it off, right? So you need to kind of work with either you know your noise model extremely well, or you somehow cross-correlate two detectors. So maybe this is already the next step, but I think we first need to kind of understand the response of the detector to just make it plain wave, right? But just to kind of somewhere put on the list of questions, or here in the recording, that I think that would also be a question to answer in the future, because at those frequencies there's many interesting stochastic sources too.
Yes, for stochastic background, I think we can use the frequency sensitivity that we compute as an ideal average response for stochastic background, for example. And the thing is, for example, we can tune the resonant frequency of our cavities to, for example, get the cutoff frequency of the stochastic gravitation of a stochastic background. And if we have the 5 first mode and we have only the first mode really activated, we can measure the more or less the cutoff frequency of such a stochastic background.
Okay.
I don't know if Sébastien has something to say.
This is something
that.
Nicola is working on at the moment, but not myself. So yeah, my only question that I have since a while for stochastic background is whether we could kind of accumulate power with a stochastic background in this kind of detectors, which seems to me not so obvious if the signal is coming from all the directions in the sky. And well, this was not yet clear to me when I was thinking about this problem, but maybe Nicola has a more clear idea now.
So I think, Andy, did you want to talk about the technical challenges that are going to be important for the levitated sensors?
Sure, yeah. Yeah,
related to this, and because you before you answer, can you comment also on the fiber-based implementation that we have put in our review, but I don't know what's the state of the art.
Yeah, great question. So, so I guess there's a few technical challenges. One of them is related to, Francisco, your question. So with regard to scaling the system up to larger size. So right now we're building a 1 meter tabletop Michelson interferometer just to sort of benchmark the concept and look at the noise sources. But ultimately we'd like to have a 10 meter long or maybe even 100 meter long instrument. And so then if we're using free space optics, the cost can get quite high for a 100 meter system, for example. So optical fiber, kind of a hybrid free space fiber configuration would be one way to mitigate some of that cost if the noise in the fiber could be kept sufficiently low at our frequency band of interest. And so we have some collaborators at University College London, Peter Barker's group, who are looking into noise in fibers, for example, from Brillouin scattering. And so it's still not really, I think, determined whether or not those noises will be able to be kept at a level which would really allow us to get our design sensitivity in the fiber-based approach. But it's something that our group is interested in, and other people around the world are also looking at ways of reducing noise from Brillouin scattering. So it's a little hard to predict how far that'll get. But so that's one of the challenges, I think, just in terms of getting maximal sensitivity in large instruments, is can we do this more cheaply by using a fiber instead of a free space kind of approach. Another question we had earlier after George's talk was about the frequency range. How high can we make the frequency if we wanted to extend, for example, up to megahertz band? I mean, one thing I think that the community and possibly the broader gravitational wave community could contribute to would be if we had lower optical loss materials. So high index, low loss materials would allow us to use more laser power and therefore get more trapping frequency without damaging things or melting things. So that's one thing I think that can that would sort of expand the useful bandwidth of the levitated method. And then I think one of the other kind of technical things that we need to sort of demonstrate now, George already talked about, where we're trying to use these geometrical methods to mitigate heating from light scattering, from photon recoil heating. And so that would allow us to levitate larger masses without getting excess noise from scattering, which can also improve the sensitivity. So those are kind of the three, I think, three of the main technical things we need to work on to really improve the sensitivity and make a real, full-scale instrument out of this concept.
And then on, I think so, the BEC and microwave cavities that Nicola and Sebastian were talking about, for those you guys are gonna think about funding opportunities going into the future. But for levitated sensors, we have some funding for the prototype. And Andy, do you know what's the future of funding looking like for this type of approach?
Yeah, so right now we have sort of just a seed grant sort of thing to make a demonstration 1 meter Michelson. So based on the results of that, hopefully we will be in position to decide on the feasibility of a larger instrument, maybe a 10 meter scale type of a thing. And then in that case, we'll need to look for alternative funding. But also I think that if we can demonstrate the feasibility, it also points to the usefulness of having multiple sensors around the world in different locations. And so then perhaps some sort of collaborative proposal internationally would make sense at that point if the noise really checks out from what we're expecting it to be.
Yeah, so Valerie was asking that earlier in the Mattermost about multiple detectors. So.
Yeah, I think even at the prototype stage, it's interesting, even with a 1 meter instrument, I think to have a couple of different detectors so you can do correlations and things like that. But I think to really do more discovery potential, kind of 10 meters is maybe more of a natural scale to aim for.
So yes, scientifically building more 10 meter ones is obviously bigger, but I think it's not super trivial to build multiple 10 meters directly. So I think we should also see the value of building multiple 1 meter ones as training experimentalists around the world on how to build these things.
Well, that, and also if you do manage to extend the sensitivity into the higher frequency band, then actually the smaller instrument, actually, it doesn't really hurt you. So
yeah,
as much. So
yeah,
so I agree. There is some utility even at the higher end of the frequency band for even the 1 meter instrument is still going to give you pretty good sensitivity.
I think something that's useful for having a big network, especially that's unique to the LSD concept actually, is because our common mode noise cancellation is somewhat less clear because of course we have 2 cavities, but we have 2 particles, and the 2 particles will have different thermal noise backgrounds, right? So if you really wanted to talk of spurious signal rejection, then our signal I think actually benefits more than like a straight LIGO type for it.
Yeah, so I think all of these things, the more people we have working on this, the better for,
Yeah, I agree. Definitely more coincidence between different measurements is always good. And if you don't need to build a 4 kilometer instrument to get
and
more
a lot
instruments,
of times,
it's a good
even for noise hunting and systematics, like from the LIGO community, right? Like what the 40 meter was doing and what Geo was doing, what was happening at these other locations was definitely informative to then implement in LIGO. So, and then also LIGO, Hanford, and Livingston are always helping each other. Do you see this noise? This is what we did. Does it make yours better? So that kind of work is also good. Yeah.
Yeah, and I think to add to that, like, okay, you can like already kind of, if you're just placing bounds, right? If you cross correlate, obviously you can benefit as you were explaining, right? Because some of the common noises cancels. But if you ever get to the point of making a detection, then I think having different detectors. I mean, A, it gives you more confidence. B, it gives you information about kind of if you're actually the polarization of the mode, the direction. I mean, if you're looking at stochastic signals or kind of individual signals, right? It gives you much more information. And I think in order to claim a detection, that would probably be crucial.
Yeah, I think it's essential. Yeah, for discovery, it's essential to have more than one.
And so that was the reason for coincidence, right? That LIGO's 2 Michelsons are parallel to be able to claim coincidence. So that means that we need at least 4 to be able to map polarization properly, like two that are parallel to each other and two that are in other orientations.
Right, but you know, people have dreams about building, you know, multiple LISA instruments, you know, which is you know, like the cost of that is completely unimaginable, right? But here, I mean, you have a, you know, at least at least at the 1 meter scale, you know, at least, I mean, and then if you kind of demonstrate that it works kind of at 1 meter, right, then there's possibly also a stronger case to repeat the exercise at 10 meters. I mean, it's kind of a question of also convincing funding agencies, I guess, right, what to do in which order and in what step.
Yeah.
Question about funding. How much does it cost, one of these?
Yeah, so the prototype, it's basically around 1 million US for to commission, build it and commission it, basically. So it's relatively small scale compared to other things in this field.
Yeah, that's very good. This is, yeah, you can think about escalating it, I thought. And also Yvette's case also was a few million or so.
And I think we're running quite late, but one last thing I wanted to kind of put in people's minds, and we can talk about this in the next coming days. This is more relevant for existing detectors, like the bulk acoustic waves and levitated sensors that are closer to coming to fruition, about thinking about data. How do, in this community, what do we want to do with the data going forward? So I'll just put that out there, and we can think about it and have more conversations about that in the coming days, maybe. Okay, did anyone else have anything to say before we wrap up for today?
I think Yvette wanted to say something.
Yes, and I was like, oh. Yes, so sorry. No, sorry, I was muted. So yes, I wanted just to make a comment about funding. Last year, there was this call in the UK called Quantum Technologies for Fundamental Physics, and this sort of idea it falls there exactly into that. And well, but that you know, was already distributed. I was shortlisted. So it got very close, and now there's the second round coming, but there's very little money. So I think it's more about perhaps funding the ones that are ready and giving them a little bit of an extra boost. But I wonder if there could be more pressure from, let's say, joining. I'm EPSRC, and I guess you guys, well, the ones in the UK are STFC. If we could join together and put a bit more pressure, because there's already that sort of direction. And I've been talking to the EPSRC people about using quantum technologies for fundamental physics, and they're very interested. So if we had something similar coming from the other side, I think this could be a good plan to fund this high frequency gravitational wave, you know, projects, directions. So maybe we could have a chat about that at some point.
Definitely, yeah, we should have, definitely. Yes, and do you know how big were the grants?
Oh gosh, I think there was around 40 million, but you know, some of the projects, so for example, one of the things that they funded is an atom interferometer in Oxford, which is several meters big. And I think that took perhaps like, you know, half of it or something like that. And then there was 9, but what I could do is find the projects that were funded, the webpage, and you were not involved in any project, Fernando?
No.
Yeah, the grant sizes were about 4 to 7 million.
Mm-hmm.
Yes, yeah, that's right. And some projects special could argue that they could, you know, they needed more, but the normal ones were within that. Yes. So I think it's the right moment to push into it, because also the people in quantum want to see, okay, what can we use? They want to demonstrate that we can use quantum for interesting things too.
Mm-hmm.
And they find very attractive this sort of line of high energy physics or gravitational waves and so on. So I think it's the right moment to put a little bit of pressure on both sides and see if we can get somewhere.
Absolutely, yes. Let's talk about it. Yeah, that's very good.
Okay, great. Well, thanks very much.
Thank you.
Yeah, it's been really a great discussion.
Yes, I agree. So did anyone else have anything to contribute or ask at this moment?
I have like one really quick question for Yvette, and I hope it's not too out of field, given we were moving on in context and subjects. But I mean, there was talk about collaboration earlier between different experiments, right? And I think, I mean, correct me if I'm wrong, but portable BECs are still not very good. But a nanoparticle experiment is actually extremely easy to make portable because it's much simpler than a BEC. So I guess my question is there a BEC experiment anywhere in the world where you can just take a portable nanoparticle experiment and stick it next to it? For, you know, you said that your first goal was to put one next to the other and sort of try and wiggle one with the other, right?
Yeah, so the idea was to bring a nanobead to, in this particular project that, you know, that we got shortlisted was Adrian Arnold has his BEC in Strathclyde, and the idea was to bring a bead to that experiment by either, like, who was in, Pierre Berlot, who was in Nottingham at the time, was kind of the one who was supposed to do that if the project was funded. Now Pierre, I think, left, no? But Hendrik Ulrich in Southampton has a bead experiment, so he would also, if the funding was available for that, I think he would also be happy to do an experiment like that. But yeah, the BEC is not something that is easy to move, yeah. But the beads are, no? I understand.
Yeah, I mean, the experiments are almost so simple. It almost seems a shame not to do it.
Yeah.
I mean, especially if your distance constraint is really millimeters, right? Like that's a much bigger number than I thought you were going to say.
Oh yes, and did you see, like, I mean, that is definitely something that could, you know, I think should be done, because you don't need 10 to the 8 particles in the BEC. You need only 10 to the 6, I think, or 10 to the 5. You can see the numbers there, but the requirements that I showed to you, the sensitivities that I showed to you, you know, they are high requirements, because gravitational waves have, you know, so little amplitudes. But if you wanted to measure the you know, just the coupling with the gravity and the phonons with a little bead, that is a much simpler experiment. Yeah, I think it's basically about putting the two experiments together. Yeah.
Yeah, right. I mean, that's yeah, I guess my question is, can you take two fully funded experiments that already exist and then just stick them together without additional funding? But I guess maybe that's overly simplistic. Anyway, thank you for answering my question. I'll stop asking off-topic things now.
Thank you.
Yeah, I think there is an off-topic channel in Mattermost that I encourage people to use heavily, because nothing is really off-topic. But perfect. So it's getting quite late, and maybe we should wrap up, especially for our Eastern collaborators, for whom it's getting really late now. But yeah, thanks a lot for joining the discussion. Thanks for contributing, Indy and Yvette and Nicola, who's left now. But yeah, thank you everyone for answering.
Yeah, thanks. Yeah, really
Yeah,
interesting.
just to say that tomorrow we would use part of the initial half an hour to restart the discussion if needed. If anyone else wants to add something, or maybe there are collaborators from Australia who couldn't join. And
yeah, I think there might be people who couldn't watch Space Talks live, so they can watch them on video and then also ask tomorrow. So it would be good for people who gave talks today to stick around tomorrow in the morning. Yeah.
Okay, very good.
Perfect.
Good night,
Yeah.
everyone, or good morning.
Thanks.
Bye.
Bye.
Yeah.
Bye.
Thanks, everyone. Bye.
Cheers.